This question, it's a 1 mark question. It looks like simple and all that, but involves some very deep concepts from MRI. Okay. First of all, this question, the answer key said this is marks to all, which means like you have chosen any option, you would get marks for that, right? Do you know the reason for that?
Yes, sir.
Yes,
Yes,
sir.
please go for it.
Sir,
Sir, it will be
or.
and instead of or.
Okay. So
Both the conditions must be satisfied.
yes. So T rep and T echo are like the parameters that we could vary independently. We are two independent parameters for most situations. So this is actually should be and. Let me explain the problem. What I did in YouTube is this. So I said, okay, if TR is short long, if T echo is short long, for this combination, short not short combination, you will get T1. For short long combination, you will get proton density, and long combination, you will get T2, which is what I said. And there was a comment, and I really appreciate the student who commented it. Didn't get the logic. Great, because I did not explain the logic. I put up a table saying which combinations will give which. Okay, and of course the student was also curious, where can we find this theory? Great. So the thing is, I already had given her pointers on the references, Bushberg. But the problem here is, if you go look at Bushberg, as some of you mentioned, it's going to take a lot of time to dig through the material, specifically in magnetic resonance imaging, which is why I will try to get into as many details in MRI as possible while trying to keep things simple. Okay, I'll give the logic behind why this is the case, while while keep maintaining things very simple. Can we try that for today? That's the agenda for the rest of the class. Are we all in? I need your full cooperation. We need some hand raises. We need some answers in the chat. We also need some. I need to hear some. We need to hear some voices back. Can we go for that?
Yes.
Sure, sir.
Yes, sir.
Okay, let's do that. So in MRI, first thing is we need to know the directional terminologies. Okay, we have this main magnetic field that is applied, right? B naught. For a 3 Tesla machine, this is that 3 Tesla. This B naught is what it refers to. Okay, that is applied in a certain direction in the MRI machine. Fine. That is known as the longitudinal direction. Okay, and the plane perpendicular to this longitudinal direction is known as the transverse plane. The longitudinal direction is usually given D. It's a standard notation. The transverse plane has X and Y axis. Fine. Simple directional terminology. That's a standard in MRI. Are you with me till now?
Yes, sir.
Yes, sir.
Great.
Yes, sir.
So now, what do you think happens to the to all these protons when this MRI machine is turned off? What will be like the net magnetic field from the protons? What would that be?
Aligns to the parallel to the direction of magnetic field, sir.
If magnetic field is turned off, they will be like in different directions, right? Pointing all over the place.
Yeah, sir.
Yes, sir.
So if you apply a magnetic field, most of them will align towards the external magnetic field, the longitudinal direction. Fine. Okay. So we have a student saying that parallel and anti-parallel. What happens is, most of them go along this direction. A small percentage of the population go against this phenomenon. That's known as anti-parallel, magnetization. That's fine, but the net will be towards the longitudinal direction. Clear? Okay. Are you all with me here right till now?
Yes, sir.
Yes, sir.
Okay. So let's go further. Okay. So now this is where I have an external magnetic field. The protons, the net magnetic field of the object that we are trying to image is aligned this way. Okay. Now, what do we do next in MRI? Somehow say this. diagram shows that it starts tilting, it goes towards the transverse magnetic transverse plane, right? XY plane. Why does that happen?
Due to application of radio pulse, sir. Radio frequency.
Radio pulse.
RF pulses.
Thanks. Yeah. At this stage, we need another field. We add a radio frequency pulse to this material, to this object we are imaging. What that would do is to tilt this net magnetization towards the transverse plane, as shown here. So now this is totally in the longitudinal plane. The moment we apply the RF pulse, it tilts. There are some parameters for the RF pulse. Let's say we apply what is known as a 90-degree RF pulse, tilts and goes to the transverse plane. Fine. That's why we have this RF coil in MRI machines. Okay. Are you all with me till this point?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So now we perturb all these protons. We are in this transverse plane. Now I turn off this RF field, RF pulse. It's a temporary pulse. What would happen? Let's go. Whoever wants to speak. Now we will turn off this RF pulse. What should happen?
The protons will try to realign with the permanent magnetic field.
Okay. Thank you. That's a nice answer. And who is this?
Matangi.
Madangi. Okay. Thanks, Madangi. So she said protons will try to realign with, somehow they will try to go back to this original align towards this external beam. Fine. Okay. Now some other student, what is the way in which they would do that? How would they do? Will they just tilt towards z-axis again? What is the trajectory that the tip of this vector would take? Any guesses? Okay, Madangi, any guesses how?
So they will precess back, so in a
Yes.
spiral way.
Yes, it will almost precess back in a spiral way. What it will do is, it will spiral. Sorry, my spiral is not that good. So let's say initially this was the vector. It keeps on spiraling. 3D ends up to be this vector. Fine. So it's like initially this way, spirals and gets here. The net magnetization. I'm not talking about individual protons. I'm talking about the collection of protons. Fine. Transverse. Let's say this is the transverse plane. They spiral and get to B0 again. Say this is the longitudinal direction. Fine.
Yes, sir.
Yes, sir.
Sir.
Is
Yes,
this clear? Okay. So now this process of this perturbed magnetic moment going back is known as relaxation. That's all relaxation means. Nothing big. Relaxation means we perturbed it using an RF pulse. It's going to go back. We can look at this relaxation in now different axes. We can look at it in the XY plane. We can look at it in the Z axis. Is it clear? So this is a vector. We can take its component in the z-axis, or we can look at its magnitude in the transverse plane. Is that possible?
Yes, sir.
Okay. So now what would happen to this component here in the transverse plane? What would happen to this component over time in the transverse plane?
Will
Will
decrease.
decrease.
This will decrease. What would happen to this component in
It will increase.
the longitudinal plane? That will increase. Okay. So relaxation of this component is known as T2. The time constants associated with that is known as T2 relaxation. And of course, the physical things that are going on, all that is termed as, given a name called T2. The relaxation that happens here in the longitudinal axis is known as T1. Fine. Of course, T2 will decrease over time, or will relax. As it relaxes, it will decrease. T1, as it relaxes, it will increase. Okay. So now I am going to test if you actually followed this. Okay, I have shown some two curves. Okay, let's say this is time and this is time. This is time. Okay. So let's label them. Let's label this as A. Let's label this as B. What is the kind of relaxation that's going on in, say, figure A? What is the relaxation that's going on in figure B?
A is T2.
In A, T2.
Chat, please. We have A is T2, B is T1, A is T2, right is T1. Okay. We have this thing saying that, great, this is T2. How do you know that? Okay, initially it's like it has some value. As time progresses, as it goes towards the longitudinal axis, it becomes 0. So this is T2, and this is T1 relaxation. Fine. So most of you got it. Now, can someone guess how this relaxation is helpful in getting an image formation? Please go for it. Use your mind.
Different tissues have different relaxation times, sir.
Yes, who is this, please? Who is this? Yeah, please. Can you elaborate more? I think you're right. Can you elaborate more? Let's all hear you better.
Like if we consider T1 relaxation time, sir, in the human brain, we have gray matter, white matter, and cerebrospinal fluid. Okay.
Okay.
The white matter. If we draw the graph, if we plot the T1 relaxation time for B plot for these three, we will have different slopes.
Okay.
So from that we can find these tissues have different relaxation time, and thereby we can find we may be able to distinguish these tissues, sir, in the image.
Yes. Okay. Thanks for the answer. So what he's saying is, say this is tissue 1, this is tissue 2, the red curve over here. They will have different relaxation times. Okay. And so the rate at which it goes to 100% is different from the rate at which this goes to 100%, because their relaxation times are different. And if we were to make any measurements over here, this difference will show up as a contrast in the image. Okay. Here we won't see any difference. Towards the end, after it has got to 100%, we won't see any difference. But in between, we will see some contrast between tissue if they have different relaxation times. Are we on this?
Yes, sir.
Okay. Now let's actually see what is the case again schematically for the tissues that you mentioned. So what I have here is it goes back to the original, right? So this is T1. T1 relaxation, white matter is pretty fast. It goes really, really fast. Where is white matter over here? This white region,
light one.
all this region is white matter. It goes really fast. So we have its intensity is more, white. The gray matter in the region is, you can see it's grayish. It relaxes slower. So if we have to take any line over here, this has more intensity, lesser, least. Okay. Cerebrospinal fluid. This part is dark because it relaxes very, very slow compared to the other. That's what establishes the contrast in the image. Clear?
Yes, sir.
Sir.
Yes, please. Okay. Any doubts at this point?
No, sir.
Okay. So let's look at what happens to T2. Okay. So now these are T2 relaxations. Again, CSF, gray matter and white matter do different things for T2 relaxations. Again, the cerebrospinal fluid relaxes very slow. So if you had to take any line over here, see the difference. Then this is very, very white cerebrospinal fluid. This white matter is, relatively, where is the white matter? White matter is supposed to be dark. White matter, okay, where is the white matter here? It's pretty dark, right? All these regions. Then we have the gray matter, which has middle contrast. All this, the boundaries. Fine? Clear? Yes, thanks. Okay. So let me proceed further. Now, okay. So we will finish with this particular slide. Here is the thing. So now I am going to introduce two parameters. Let's say, you're a photographer, you have shutter speed and aperture in the camera, or you are cooking something, the amount of time that which cook make an omelette, whatever it is, okay, or a soup, okay. Let's call, so the cooking time is one of the parameters, let's say T, and there is one more parameter during cooking. So say the vessel you use or whatever, again that's a time. Okay, so we have two parameters to control this MRI process. The set of figures in the left, what are those figures? It is T2, right? This is T2, this is T2 relaxation, T2 relaxation, right? They are all going to 0.
Yes, sir.
This is T1 relaxations. Now, let's say these two parameters can be independently varied. We will look at what they are in subsequent, classes. But we choose T such that we measure here, and TR such that we measure here. Which of these two signals will be differences will be highly reflected? Which of these differences will really show up?
T1.
T1. T1.
Yes. So for this combination, very short TE, intermediate TR, T1 will show up. The differences in tissue T1 relaxations, that difference will show up, and this is known as a T1 weighted image. Okay. When you have a long TR, and again this is long
T.
This is long TA, suppose. What is the kind of image we will get here?
T2, sir. T2 weight.
Okay, we will get a T2 weighted image. Okay, and finally, we get some minor difference over here and some minor difference over here. What will be the resulting? So neither of this is really enhanced. Both of it have some contribution. What will be the kind of image we get?
Proton density.
Okay, what is proton density is, so the signal we get depends on the amount of protons that is there in each of the tissues. If gray matter has more number of protons, more number of hydrogen for some reason, we'll get more intense image. So this is known as proton density image. Fine. So this combination will give T1 weighted, this combination will give T2 weighted, this combination will give TR weighted. Short TE, long TR will give proton density. Fine.
So I have a doubt.
Yes, please.
So is the spin density image same as proton density image?
Spin density.
We are considering the spin of the proton now, sir. So there may be proton density is actually spin density, right? Protons
Proton
are
density. Okay. Again, I haven't come across this terminology. I usually have come across proton density. I can go back and check and get back to you. At this stage.
So in proton density's case, then which out of CSF, gray matter, white matter, which will have more number of protons? The one
More
with
number of protons. So first of all, in proton density, this amount of contrast will not be there. We'll just see some detail. It will all be like more grayish. I can send an image to actually answer you.
Okay.
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 Okay. So at this point, what we did is we understood what is T1, T2 relaxations and how this weighing shows up. What we took for granted is what is this parameters, what is this TE, what is this TR. Okay. In the subsequent classes, we'll go back and probe the MRI, all this MRI process. We'll answer what TR and TE is. Okay. And for today, this is what we actually hear is a summary of things that we looked at regarding MRI. And all these details are involved in that small question, 1 mark question, asking this combination will give which weighted image. As we proceed further, we will really nail this. We'll learn these things properly as well as many more things clearly. Fine. But for today, this is where I wanted to stop. Fine.
Okay, sir.
Any questions, comments? I'll send a proton density image just so that how it looks, and I will also go check if proton density is also called as spin density. And and of course I left out what is TR, T echo. And there is something known as T2 star, where we need to go deeper into some of the details of T2. We'll also do that in subsequent classes.